rectilinear motion. If you recall back to previous units in this course, we talked about the motion along a linear path, and this was called rectilinear motion. And from that, we concluded that we had some position function s of t, and we said that s prime, the first time derivative of s, gave us a velocity function, and the second derivative of the position function gave us the first derivative of the velocity function, which gave us an acceleration function. And we used derivatives to help find the subsequent rates of change, the rate of change of the position, the rate of change of the velocity, to get our functions. Well, now we're going to use integrals to essentially go backwards, in that we can find that the integral of a will yield a change in v, and an integral of v will yield a change in s. And we've kind of talked about this slightly in previous topics, but if, say, we have some velocity function v, and it's a function of time, and we want to integrate this from, say, some time a to another time b, it doesn't matter what it is, well, it's going to give us and we're doing that with respect to t, it's going to give us the antiderivative of the velocity. And we know the antiderivative of a velocity function is going to be the position function plus some constant. But since we have bounds here, we're going from one point A to another point B, then we know that this is simply the position of B minus the position of A. And this tells us a change in the position, which is really what we call a displacement. Okay, so we know that when we integrate a velocity function from one given time to another, that gives us a change in position. Now, where we need to differentiate here, and I use that word as meaning finding a difference, not as finding a derivative, is we need to differentiate between the word displacement and distance traveled. Okay, because these are two different things. And let me illustrate the difference here. Say you start at some position right here, and you travel 10 miles north. Okay, so we're going 10 miles north, and then from that position you travel another 5 miles east, and then you travel 10 miles again south. And if we look at the displacement, what have you changed? What's your change in position? Well, your change in position is simply this 5 miles east. But the distance traveled is different. You traveled 10, then you traveled 5, then you traveled another 10. So your distance traveled is 25, your displacement is 5. So we want to be able to use calculus to help us find this, and we can with a simple adjustment to our velocity function. So we know that displacement, this is displacement right here. We can find displacement just by integrating a velocity function with respect to time and evaluating at our starting point and ending point. Now, to find the distance traveled, and this is an important part, the distance can be found by integrating the velocity function, once again from A to B, but we want to integrate the absolute value of the velocity function with respect to time. All right, so that only tells us the distance traveled. And these results could sometimes be the same if it's a positive function over the interval, but if especially if the function changes sign over the interval, these two results are going to be different. Okay, the displacement and the distance. So how do we arrive at an actual position function? So we want a position as a function of time from a velocity function. Now, we know that to go from position to velocity, we simply take a derivative with respect to time. And so naturally we would think, well, to go back, we would just have to integrate with respect to time. But the issue with that is we're leaving out our initial condition. So we have to understand that in order to go from velocity back to position, we have to know an initial condition. And typically we like to have what is s of 0. If we know what that is, then we can go back and write a function. And in fact, that function will be, given some velocity as a function of time, the position function as a function of time will equal s of 0, the initial position, plus the integral from 0 to t of v of x dx. Now you might ask, wait a minute, if this velocity is a position of time, why do we have the variable x in here? Well, keep in mind, basically what this is saying is we're taking the antiderivative here, going from 0 to t, and we just want to change our variables. We can't have the same variable of integration as we do as the variable in our bounds. So this x is just a dummy variable that we're going to use in terms of our integration. So this is to find any position function, okay? And likewise, we can use the same thought to take an acceleration function as a function of time, and we can find a velocity function. And so the velocity function, given some initial condition that initial velocity is known, okay, so we know what this is, the velocity function is going to be that initial velocity plus the integral from 0 to t of a of x dx. So we're using the same logic that we use to find a position function from a velocity to find a velocity function from an acceleration. It's using the same principles and the same relationships of the velocity is the first derivative of position and acceleration is the second derivative of position. We can go backwards if we have the initial conditions and create new functions using integration. So let's use an example here to illustrate all of these principles here. So let's say we have a cannon, all right, and it's going to fire, and this cannon's starting, let's say, 30 meters above the ground here, all right, and it's firing a cannonball straight up in the air at 300 meters per second. Okay, so it is a distance of, say this is the ground, it's a distance of 30 meters above the ground, and it's firing a cannonball 300 meters per second straight up in the air. Let's say the only acceleration acting on this cannonball is the acceleration due to gravity, which we'll say is a constant negative 9.8 meters per second squared. All right, and we want to know a few things. One, we want to know what is a function that relates the velocity to time. So we want to know what is a possible v of t. And we also want to know what is the distance that this cannonball travels. So we want to know what's the distance, okay, that it's traveling in the air. So first, let's find v of t. Well, we know v of t is going to equal the initial velocity plus the integral of our acceleration function. And remember, we're going to put in a dummy variable here from 0 to t. All right, well, it just so happens that our acceleration is constant, so this is going to equal our initial velocity of 300 minus the 9.8 meters per second squared. But if we integrate that, we're just going to get 9.8x, and we're going to integrate that from 0 to t, and so really we get 300 minus 9.8t. So that is our velocity function. Now, in order to find the distance, we have to define what distance we're talking about here. And since I made up the question, I'm going to define it right now as, let's just say, the distance from the starting point to the highest point. All right, so how high does this get? Well, we have a few ways we can do this. We can either find a position function and see what the position is at that point, but then we'd have to find a time, or we can look at the distance traveled using the absolute value of the velocity. And so we're actually going to do both here. And first we're going to find a position function. So if we want a position function, we need s of t. And we know that's going to be the initial position plus the integral from 0 to t of our velocity. And so in this case, it's going to equal the 30 plus the integral of the 300 minus 9.8x, which is going to give us 300, let's do this, 300x minus 4.9x squared, and we're going to evaluate that from 0 to t, all right, which gives us a position function of 30 plus 300t minus 4.9t squared. So this is our position function. Now, in order to evaluate this, we need to know, well, where or at what time does this reach its highest point? Well, when it reaches its highest point, its velocity is 0. So let's go ahead and get some more space here. So we know our position function, let's write it back down here. We have 30 plus 300t minus 4.9t squared. And we knew our velocity function was 300 minus 9.8t. Okay, so we want to know, when is this reaching its highest point? Well, that happens when this is equal to 0. And so that happens when we have 300 divided by 9.8, which is, let's say it's approximately 30.6 seconds. Okay, so this is the time that it's at its highest point. And so we want to evaluate our position function at its highest point. So the position is s of 30.6 is going to equal 30 plus 300 times 30.6 minus 4.9 times 30.6 squared. And this gives us a position of approximately 4,622. Okay, so this is 4,622 meters. Now, that is our position. Our question is, what is the distance traveled? Well, if we started at a position, s of 0 is equal to 30 meters, and we ended at a position of 4,622 meters, we can subtract these two to get 4,592 meters to get our distance. Now, you may notice that, wait a minute, are we making a poor assumption here? Well, we are making an assumption, and actually it's okay, and we're going to confirm it in a second. The assumption we're making is that really what we calculated here is the displacement. And so the assumption we're making is that the displacement is equal to the distance traveled. And you can't necessarily always assume that. Now, I did that because I knew what was going to happen in this problem, but you can't assume that the displacement is going to be the distance traveled. So how do we know for sure how we can find the distance traveled? Well, we can take the integral of the absolute value of our velocity function, v of t, okay, and evaluate it from our 0 to 30.6 seconds. Okay, so the absolute value of, this is going to be the integral from 0 to 30.6 of the absolute value of 300 minus 9.8 t dt. And we can ask ourselves, we can actually look at, okay, well, what is this function like in our interval from 0 to 30.6? Well, at 0, we have a positive function. It's the absolute value of that. And at 30.6, we get about 0, and so we take the absolute value of 0, which is just 0. So nowhere in this interval are we negative. So this really acts like the integral from 0, 30.6 of 300 minus 9.8 t dt. And we can get rid of the absolute value because we know that that quantity is always positive within this interval. And if you do the integration, I'm not going to do it all right here, but you're going to get approximately that same value of 4,500, let's write it here, 4,592 meters. All right, so in this case, our distance and displacement is the same. Now, if we have a function, if we have a velocity function that changes sign within our interval, then this is the only way to find the distance. Now, because our velocity function didn't change within our time interval, then we could use either technique. Now, where this would change is if I asked, what distance is traveled until time equals 50 seconds? And so then you would have to use the absolute value, and you'd have to break this integral up into two integrals, from 0 to 30.6 and from 30.6 to 50 to find the distance traveled. Now, what this allows us to do is to make a general statement that integrals can give us a net change, because we saw the direct application of this net change, and the change in velocity plus the initial condition can give us a velocity function. We found the change in velocity from integrating acceleration, and likewise we found a change in position by integrating velocity. So if we have some function, let's just call it f, okay, some function f of x, we can find the change, the net change in f of x from a to b by taking the integral of f prime of x from a to b, because that's what we were doing. We were just doing that in the previous problems, and that the change in position was going to be the integral of the velocity function from a to b. And what is the velocity with respect to the position? It's the first derivative. So taking the derivative of a function and then integrating it from a to b gives us a net change. And we're going to use this